Hello, everyone. Welcome back to another episode of Dangerous Cosmology. This is Nightfall Zero, your host tonight. And here with me, we have quite a few people today, actually. I'm happy to see that. We have Commander Eraptor.
Hello.
Raptor. That's
Just
how you
Raptor.
pronounce the name, right? Raptor. Okay, that's easy. Just a Raptor.
Yes.
Commander Selfish Spy.
Hello!
And of course, as usual, Commander, that
Just a
Michael,
Raptor.
who is handling all the technical side of these communications.
Yes, this time without issues, for now.
For now, yes. And you also have a video stream, right, on Twitch?
Yeah, that one is being taken care of Raptor. He's live now, I hope.
You also have a video
Yes,
stream. Okay, the Raptor is doing it. And then we
Also,
have
I will be
also
watching the
Commander Thor Wotanson.
Hello.
And as usual, we have our good doctor, Commander Shoba.
Hello.
Shoba and me, we're currently broadcasting live from the cockpit of the Red Comet. We are 55 jumps away from the next waypoint. And we're trying not to crash, because I actually got quite close to crashing. I don't know about you guys, but have you been visiting the points of interest?
Not
No,
too
I
much,
haven't,
actually.
I'm ashamed to say I am not even close to those.
Yeah, I'm the same. I'm ashamed to say that I've not even started on the way to the next waypoint. I've just got too much stuff going on.
I'm actually
Yeah.
flying from Colonia, kind of flying the direct route from Colonia to there, because I was at Colonia for a week.
Right, because I was wondering, I was reading and listening in the other day about the code black that happened from the whole seals, and I was wondering, is it fair to call for help from the whole seals if I am sitting at 99%? Because that bothers me.
You could definitely ask in the channel, say, hey, if anyone's nearby, if you want to, you could come repair me. But it's not a big deal. It's
not.
kind of
It just annoys me because it's not 100. It's just annoying. I don't.
Yeah, I would
like
say if you're bugged, just wait till you get to the waypoint and then say, hey, if anyone's in system, do you mind shooting a
I could
limpet
do
at me?
that. Now there was this system, the point of interest. I forgot how it's called, but it jumps you straight into a black hole and it drops you out of supercruise, and you just get damaged.
Was
That's
that Ivory and
terrifying.
Ebony?
No, that one I avoided. I read the entry in the log, and I just nope. I'm not going there. I'm too scared. It was the other one, the one that's close to the previous waypoint. I forgot the name, but
I am there
some
now.
of the. Yeah, what was it called?
Let's see. It's called.
Well, anyway, it was just scary. I wasn't expecting to be dropped off out of Super Cruise so fast, and so I was wondering if the whole seals can help. But anyway,
Gate Coaster Remont.
yeah, maybe that was the one.
I nearly crashed too this week. Found
Yeah,
the-
don't do that. You're kind of needed. If you crash and die, then it's going to be a problem.
I can just join one of you guys, right? I can be a
Well,
co-pilot
not if you're
instead.
dead. That's not going to happen. Anyway, thank you again for joining us tonight. I know that the past few weeks you've been busy, but as usual, you managed to take a couple of hours each week to entertain us and our listeners.
Well-
Tonight's topic is going to be the early universe and what I marketed as the first 5 minutes after the Big Bang. Now, it may not 5 minutes
No,
exactly, but
absolutely not.
cool. Well, I solved it that way, so let's try to keep it that way, okay? But yes, we're going to talk about what exactly happened after the Big Bang and the very first few things that happened and that formed after the Big Bang. That is the topic for tonight. We have gathered quite a few questions, but of course, as usual, we will be taking them live, both on the astronomy channel of Fleetcom and on the interview questions channel on the Distant Radio Discord server. So if you're not there yet, please join, contribute, listen in. If you have friends that are playing now and are deep in the black, tell them to tune in if they want to learn a bit more about space and science.
Or Twitch. Twitch is fine too.
Or Twitch.
Yes.
Yeah. If they also want
I'm
to
watching
see,
the chats.
if they want to see Raptor doing Raptory things. So, let's start with a question from me, actually, which is that I would like to consider an introductory question to the topic for tonight, because we had a past episode about the cosmic microwave background, which is the farthest thing, quoted, that we can see.
Yep.
So, starting from there, when do we start to see something else, and what do we see exactly?
All right. So let's go from the start. So from the point where matter is as dense as it can get, so if you compress it to the limits of what the laws of physics as we know them currently allow, when you just let the matter cool and do what it wants to, it takes about 300,000 years until you get to the CMB point. That is, the original matter becomes transparent. And so that first light escapes and it reaches us many years later. So that's the first observable thing after the Big Bang, the CMB, which is not that close to the start. It's still 300,000 years. Then after that, there's a long period of time called the Dark Ages, where there are no objects in the universe, there's no stars, and baryonic matter and dark matter are both just floating around, still too hot to form anything, because as some of you probably know, the hotter something is, the more it resists being pulled. Heat is random motions inside of a material. So if some matter is really hot, it will not respond to the pull of gravity. So it will not immediately form stars. It takes a long time. Actually, it takes about 100 million years, we think, for the first star to even be able to form.
Okay.
So during that very boring time of the Dark Ages, there is not much to see. Although there is a big discovery that was made, that was claimed a few months ago, that everyone is really rushing to be the first to see, which is called the 21 centimeter background. So that's in between the CMB and the first stars that we can see much later. There is this signal called the 21 centimeter background, and what that is basically. Is if you have some neutral hydrogen sitting around, just a happy proton and a happy electron going around the proton, sometimes it does a very rare thing where it emits a forbidden transition and at a specific radio frequency, 21 centimeter exactly. So just by sitting there, it will occasionally emit that type of light.
What do you mean forbidden?
So in quantum mechanics, some transitions are very likely and they're allowed like in normal practice, like the LCDs in your screen that you're all probably looking at right now, always emit the same color because that's their preferred way of transitioning and emitting light. But some transitions require very specific setup, so they're very unlikely to happen. So that's one of them. They're called forbidden. They're not really forbidden, just like really rare. For example, if you take a hydrogen atom and just put it in a lab, if you don't do anything to it, it will take on average, I think, 14 million years to emit this type of light.
Wow.
So one atom, that's how long it takes. It's a very rare transition. But if you shuffle it a bit, that goes down to a few hundred years. And if you have a lot of them, then it's likely that at least one of them will emit it. So that's been tested in our labs very, very well. It's a very well-known property of hydrogen. So if you have enough neutral hydrogen, like you did in the early universe, before there were even stars, it would emit a bit of this light. And we are actually getting to the point of seeing that. It's really at the edge of detection. We have about 5 experiments rushing to be the first. And there is one claimed detection that's a bit suspicious, and not everyone really believes it. But the first claim of seeing this signal came last year.
So it's basically RNG.
Well, not really. The way it's distributed across the sky has been predicted quite clearly.
Ah, okay.
So we know kind of what to look for, what it should look like. It's just to see it is a challenge.
What would be the frequency? Would that also be redshifted way the hell down by now?
Yeah, so you multiply the frequency of the 21 centimeter by the redshift that it's at, +1. So you get a whole range of radio frequencies. That's the cool thing, right? So the closest you are to the CMB, the higher your redshift is. So the one that's very early hydrogen will be at a different frequency than later hydrogen. So you can actually map all the epochs in between during the Dark Ages, what the matter was doing.
Oh wow, that's fascinating.
Yeah, it's really cool. Very hard to do, though.
Yeah, so as long as there wasn't enough interference in the medium of the universe, so I imagine at some point there was a density to the universe that didn't allow this radiation to get past, right?
It's even more simple than that. It's just that neutral hydrogen got completely destroyed by the first stars. By the end of the first billion years of the universe, it was all gone. It has not really existed since. Just because it's very easily destroyed by X-rays and UV. And if you have a lot of stars and a lot of quasars shooting UV through the universe, it's all going to be destroyed pretty quick. That's what's called reionization.
So it was atomic hydrogen, not molecular hydrogen?
Either molecular or neutral, but not ionized. So the electrons and the protons were bound. That's the crucial point.
Oh, okay, that makes sense.
Yeah. So nowadays, you don't find neutral hydrogen just floating around the universe anymore. It's all been split up, all the electrons are free. So yeah, so that's the next thing after the CMB that people are really looking for, the 21 centimeter background, with one dubious detection.
We're still looking for it.
Well, it depends who you ask. There is one experiment that says basically they claim to have one. Right? It's called the EDGES experiment.
The what?
That's the name of the telescope that got it. EDGES.
EDGES.
It's some abbreviation. It's always abbreviations, isn't it?
Okay.
And they claim to have seen it. It's roughly at the correct place, correct frequency, but it's a bit too strong. And their experiment isn't particularly well designed.
So we're still in the realm of, not entirely confirmed yet.
This one's not confirmed, but much effort into finding it and modeling it and predicting.
I don't know. I'm sure that I hope that it will be actually confirmed. That if we want to actually find the earliest object, apart from the CMB, if we call it an object, that is actually confirmed. What is that? Actually, it's the galaxy that was found by my team. What?
Bit of self-promotion here. Yeah, so the most distant confirmed object from the Earth is a galaxy called JD1 at a redshift of 9.1. So the light from it has been stretched by a factor of 10 by the time it reaches us. And that was found by Nicolas Laporte and some other guys from my team in UCL, I think, last year.
Wait, so you're saying that... Okay.
And that's just the most distant galaxy that we can see. So it's an actual object. We can see its shape, we have some information about it. Although, further than us, there are two unconfirmed objects. So there is a galaxy that claims to be at a redshift of 11, but it's not spectroscopically confirmed.
Yeah, actually, I read about that because, of course I know that you have a video on YouTube about this JD1 galaxy, but I have read different contradicting opinions about what the farthest galaxy actually is. And as you're saying, there are others who claim that other galaxies are older.
Just one, really. There's only one claim.
But you're saying that they're not confirmed?
No, not to the same standard. So we have right. How do you know if something is a high redshift object? It's a difficult question.
It's very red.
Well, it's very red. Correct.
Yeah.
It is very red.
Easy.
It is actually very red. So that's a start. But far away galaxies are not the only thing that are red. You also have like brown dwarfs. They can be really red, or particularly nasty, faint red dwarf stars. They can look really red. They can confuse you. So to overcome this confusion, we have a standard in high redshift objects astronomy, which is that we need to see specific transitions, so emission lines or absorption lines from these objects, because those you'd never see in stars. So if you get one of them, you are confirmed beyond doubt that what you're looking at is not only red because it's far away, it's actually far away because you can see these emission lines that are at the same distance as the rest. So that's kind of the standard. And unfortunately, the two objects that have claimed to be further than us were found by different techniques that are much less reliable.
Okay.
So they did not have these emission lines. They only had the color.
But I mean, how does the science community go? When deciding these things, you're saying that you have a standard, yet you have groups who claim things. How does it work? Is there an actual line that everywhere scientists and the scientific community at large says, okay guys, you're claiming this, but until you prove this and that, it's not going to be true?
No, I mean,
is there?
We don't speak of truth when we talk to each other.
No, Mel. Let's talk about confirmations.
Okay, so when we discuss these things, we use more technical terms.
I'm sure you do.
So JD1 is the most distant spectroscopically confirmed source. The GNZ11, I think, is the most distant candidate.
So it needs to be elected.
Well, it needs to be confirmed.
Yeah. So
having spoken to those guys personally, when you see them and they give talks to other scientists, they're very clear about what the caveats are and what extra work needs to be done to confirm it. It's just when you go to the public and you want to write a big thing for a newspaper, you have to dramatize it a bit. And it's definitely a very special thing they found. It's in any case something never seen before. Even if it's a brown dwarf, it's definitely something special. But they wouldn't claim it's confirmed when it's not. But that's not what they say.
Yeah, I don't want to downplay, of course, the work of any scientist.
I get what you mean.
It's just that, sometimes you read headlines. I think I mentioned this in one of the previous segments.
Yeah.
Sometimes you read articles online or even on physical newspapers where there are those sensationalists titles that most distant galaxy found, and they don't even go deep into explaining that they're not exactly confirmed following the standard procedure.
It depends like what level you're pitching at. There's nothing wrong with promoting your own research.
Unless it creates contradicting information, because then someone may say, oh, but I read that galaxy is in fact the most distant one. So, shouldn't the press, and maybe by extent even the actual teams who convey the discoveries to the press, be more precise about it?
I don't know. The more precise you are, the less people read,
Fair.
That's true.
It's a mix, I think we all do our best, and sometimes it is in the details, and sometimes the details take long to explain.
I know. So JD1, you actually worked on that personally?
A bit. I'm not on the discovery myself. My team is.
Okay.
I worked with it a bit. People tend to be a bit hoardy of their data if it's very interesting. I wasn't there when they found it. I joined the team halfway through. So I didn't get to be, on the main paper.
So basically, to recap, the first object after the CMB is a galaxy.
That we currently see.
So there is nothing that's not a galaxy that we can see older than this JD1.
Well, there is a candidate gamma ray burst. So that's another thing you can say.
I'm talking about confirmed stuff.
Confirmed stuff is a galaxy.
Okay.
There is a good candidate gamma ray burst at redshift 9.4. And so that's basically a very rare event that happens, usually a special type of supernova, or we don't really know how gamma ray bursts happen, but it's some violent event that emits a large amount of every radiation. So from X-rays to infrared, some catastrophic event that emits all radiations. And for a brief instant in time, it's bright enough to be seen at that time. But it doesn't last long. So that's kind of the compromise you get.
So I guess that would That would make it difficult to confirm, wouldn't it? Or do we see more of an echo now?
You have to be a bit lucky to confirm it. For example, if the light goes through something, like a very faint galaxy that you wouldn't see otherwise, if the light from the burst goes through, that will leave an imprint. So you will at least know that the burst had to be behind such and such redshift because of the thing it goes through. So it's kind of luck.
So we're kind of just watching it bounce off of things now?
Yeah. So we see it go through things. It's powerful enough to shine through galaxies.
Damn.
Or through anything, really.
So gamma ray bursts also pretty dangerous, right?
Yep. They're pretty dangerous. If you were close to them, you'd be in trouble.
By close, you mean neighborhood galaxy?
If there was one in Andromeda, we might be in trouble.
Yeah. So
Okay,
close here is a relative term.
Those bursts happen because, due to an explosion or due to something else that causes them, like a body of some sort, or they can just happen because of no reason.
We're actually not sure. Yeah, so it's actually one of the current kind of mysteries in astronomy, I guess. No one is really sure what causes gamma ray bursts. So we think it might be to do with collisions of neutron stars, or accretion by black holes, or collisions of things. But the truth is, we don't really know. We just know it emits an enormous amount of light. They don't prefer any part of the sky in particular. They can come from anywhere. And
so we can see a lot of them.
Violent. Yeah, we see quite a lot. We've seen quite a lot of them, but we don't really know.
But we don't see the source.
Sometimes you do. I think once, not so long ago, we got a repeating one for the first time. We got one twice from the same place. And a few of them we have seen, they come from galaxies. So you look after the fact, you're like, oh, there's a galaxy there.
Well, I don't know. I would say aliens.
It's actually been suggested. There was a serious paper about this.
What else could it be?
There was a semi-serious paper about this from genuine researchers on could it be, if you had could it be provoked by jumping to hyperspace or something like that?
I mean, that sounds like a pretty dangerous way of travel. Oh no, I jumped to hyperspace, 2 galaxies too close to my home system, and now everyone's dead.
Oh, what?
But it's a very powerful high wake. You just try to...
I'm just coming up with this, but drive failure?
Could be.
And you wipe out life in your home galaxy, right?
Right. Let's hope you...
That's the thing. That is the solution to the Fermi paradox. We can't see life because the first time they try to jump, they kill the entire galaxy. So that's no one actually realizes that's a side effect of jumping. It's just a very powerful gamma ray burst that kills all life.
Yeah.
But hey, at least you jumped.
Except for maybe the poor schmucks in the spaceship. Who knows?
The version I'd heard of that is that when they try to advance their civilization, it's like at the push of this button we will advance so far, then they push the button and they die. That's the version I'd heard.
Yeah, death through warfare.
Mm-hmm.
Well, there are multiple solutions that actually could apply.
Fermi paradox is a nice little whirlpool we can all get sucked into some other time, probably.
Yeah, it's not the topic for today, but also I'm not sure if...
I think the Fermi paradox could make a good topic for next time.
Well, I think it came up a few weeks ago.
Yeah, but we never got deep into it because it's
There's not that much to it.
Talking about those solutions which are most likely and stuff like that, I'd like that.
Okay.
We can think about that, yeah. But in the meantime, so galaxies, then of course I guess that it's more galaxies and even more galaxies, right? And galaxies all the way to the present.
There's also quasars, so you hit quasars at some point. Yes, quasars.
Because I know it is your area of expertise.
Absolutely. It's what I spend most of my time worrying about. High distant quasars. So the most distant quasar is currently at 7.5 redshift. So it's just at the edge of the first billion years.
So quasars are not galaxies.
Quasars are in galaxies, but what you actually see is a supermassive black hole at the center that's currently eating, so it's active. It's what we call an active galactic nucleus, or AGN. And that's shining hundreds, thousands of times brighter than the galaxy around it, so you only see the supermassive black hole.
But there must be a galaxy for every quasar.
Yeah, well, definitely at later times, all galaxies that we see have a supermassive black hole in the center. You don't see just supermassive black holes, but also you need the galaxy to feed it in a way. It channels gas to the center.
So you're saying that at the beginning, the black hole, like in the past, Sagae was feeding?
Sagae had at least one quasar episode. We know that because there's these big radio lobes on both sides of the Milky Way. So above and below, there are these big bubbles, and that we think were pushed out by the activity of Sagae star some time ago. So yeah, probably the Milky Way was once a quasar.
Okay.
But there's also a sort of nebula around Sagae, right? Like a sort of explosion.
We're expecting Sagae star to probably come back online. So we were expecting it because we saw this this big gas cloud that seemed to be heading straight for it. We actually got quite excited. You know, it's gonna feed on it. It's gonna light up.
It's going to kill everything.
It's only a small cloud. How bad can it be? You know, black holes gotta eat sometimes. But in the end, it missed. So we were quite disappointed.
Oh, so it's not safe. So we're safe.
Yeah, it's gone past now. It came quite close, but we think that at the center of the gas cloud, there was actually a star, like a small star holding the nebula together, but it didn't break apart exactly in the way we expected it. It kind of stuck together. And then it just like flung past, just getting a bit deformed instead of completely consumed.
I mean, how much of that could have been the gravity of the gas cloud itself?
If there wasn't something in the center, it should have been eaten. At least half of it should have fallen in. So by the fact it missed, it was more dense than we expected.
That's really annoying.
Hard to know from...
So
yeah, but you know, it's what you get when your gas cloud is 10 pixels on the screen. You don't really know how heavy it is.
Since we were on the subject of quasars and gamma rays, I'm going to take a quick question from Shaggy Dog. He's asking if supermassive black holes can release gamma ray bursts when they eject quasars.
They don't eject quasars.
Yeah, no, I mean...
They are a quasar. They emit gamma rays. Well, at least some of them do. But the gamma ray burst is actually more powerful than a quasar for a brief instant in time.
Really? I thought quasars were the most powerful thing ever.
Things that can last, by far. But gamma ray bursts for a split second, usually less than a second. So split second, actually a few milliseconds. For a few milliseconds, they can exceed that. But they die off super quickly, while quasars maintain it for millions of years. So...
That's impressive. So... those bursts go from 0 to max energy in a fraction of a moment.
Yep.
And then they just vanish.
Yep. And we don't really know what they are. So that's reassuring.
Maybe it's a glitch in the system.
Probably a collision of neutron stars.
I don't think we have to worry about them, because if we ever get one close enough to do any damage...
Sorry, you cut. What were you saying?
You dropped off.
Oh, I said I don't think we need to worry about it, because if we ever get one close enough to do any damage, we won't notice.
Maybe.
Unless it's a quasar.
Quasars are pretty bad too. If there was a quasar in a galaxy close to us, it would be a bit of a problem. Right. I mean, if you think about it, in terms of brightness, let's see.
Well, it's we can still observe them. I mean, I guess that the farthest they are, the harder they are to analyze. So, what is the closest quasar that we could observe without dying?
Oh no, there's a ton of them close to us actually, but they're on a scale. They're not all equally powerful. Actually, the ones early on are puny compared to some of the later ones. So
really?
You may not know this, but our universe had a bit of a hissy fit. So during about 3 billion years old and 7 billion years old, it went through puberty. And that's when half of all the star-making resources ever were used up. during this, what we call the golden age of star formation, or the golden age of clusters.
Had a growth spurt.
It had a growth spurt, and then it died off very, very quickly. Kind of like teenage. Actually, quite a good comparison.
And was it also very edgy?
It was very edgy. It was making the biggest and brightest galaxies and the most powerful quasars and everything.
That's not very edgy. You need to make a lot of black holes to be edgy.
Yeah, and
the
fidget
biggest black
spinners.
hole, so
Just giant
And
cosmic
spinning
fidget
fast.
spinners.
pretty much.
But they're spinning fast, okay, so it's fine.
Yeah.
I guess.
Pretty
I
edgy.
would've-
And
I
that's when you
would've
find the monsters.
I would have said if you want to be edgy, you would have to have done like hypernovas.
Hypernovas are pretty cool too, but they're kind of understood.
Well, you make stars explode and then you make black holes. So you do everything.
Hypernovae are pretty cool. So they're like a supernova on steroids. I'm
So
not
it's like
entirely
the-
sure what causes them either.
It's like the overachieving jocks of supernovas.
Yeah, they're like showing them up. We think it's because they're both spinning fast, have strong magnetic fields, and they end up in a black hole at the center. And that somehow gives a kickback that makes them 100 times brighter than a normal supernova. But we're not really sure. They're pretty rare. But cool.
Well, if you don't mind, I'm going to take a couple of questions that we received today. I was afraid that we didn't have enough. We still don't have many, but somehow you guys all woke up in the last hour before the show. So at least we have something to talk about. And Rusted Bulk Mike, another one of our aficionados, is asking, what are your thoughts on the work going towards going towards looking for the imprints of gravity waves from the first black holes in the CMB? Maybe you can interpret this question
I can
better
interpret
than
this
I am.
question. Actually, that came up in the CMB topic. I think we had this question.
Did it?
What can we learn in the using the CMB? What can we learn about what was before? That's what it's
That's
related
true,
to.
actually. Yeah, no, you're right.
Just to summarize, in the CMB, if there were black holes already before, like some theories predict, already before the CMB was emitted, then matter would preferentially be attracted towards those black holes. It would create a pattern of convergence, what we call polarization in the CMB. So it's something in addition to the temperature of the CMB. We measure the temperature very, very well. Polarization is a lot more difficult, and we're currently doing it using the South Pole telescope. But we haven't found it yet. Basically, the more primordial black holes you have, the stronger this polarization feature should be, but we haven't found it yet. So we're putting better and better limits on how many you can have.
Okay, yeah, no, I remember you mentioning something along those lines in our previous talks. So, yeah, as a reminder, everyone who is listening, we have all the previous Dangerous Cosmology segments uploaded and available at any time. So if you want the link, just read the radio chatter. Someone will write it somewhere there. So if you missed any of the previous episodes, just make sure to have a listen to it. Plenty of good information. And maybe you will find the answer to many questions.
I found the... Oh, sorry.
No, go ahead.
I've worked out the thing I was trying to do as a ballpark of how bright a quasar is. If the brightest quasar that we know was about 25 parsecs away, it would look as bright as the sun
Holy shit.
from the Earth.
You just Googled that though, right?
I extrapolated from a Google, because
Okay.
Google doesn't know what the brightest quasar actually is. Wikipedia is always behind. If I had time, I would correct so much of it.
Really?
Yeah, it really is. Wikipedia is terrible.
So we live in a world where Wikipedia is not reliable?
What?
Especially about like, extremely...
Wikipedia is more wrong the more technical you go. If it's really, really niche things, it tends to be incomplete. Or like just be copy-paste from articles and not make
you
sense.
Scientists should take some time or hire someone proper to update.
Sure, give me money, I'll hire someone.
And don't ask me, ask the country, I guess. Ask the Queen.
I'll have a go.
If I become a dame...
A dame?
That's the equivalent of Sir in Britain.
Ah.
Yeah.
Can't you be a paladin? It's cooler.
No. I can only be a lady or a dame.
Okay, that's boring.
Yeah.
Sir is pretty cool. Well, if I do...
Yes, Sir doesn't really fit
I will use all
you,
my
but-
money to hire more people.
Cool. To update Wikipedia.
Yes.
Alright. Can't you just use some, like interns?
Nah. Our interns are busy doing exciting things.
Wikipedia is exciting. Anyway, Thor. You
Yes.
have a few questions, right? Do you want to ask them?
Yeah, stand by 1 second.
You don't
I
remember
gotta-
your own questions.
I just gotta dig to them. So one of them was regarding the consensus on micro black holes. I believe I heard somewhere that there was a theory going around of micro black holes in the early universe that they all evaporated. I was wondering what the current consensus on that and what you thought about that was.
Yeah, it's related to the polarization of the CMB thing. So they would leave a very specific imprint. We're definitely looking for it. It would be really exciting if we found it. There was a claimed detection some years ago, which turned out to be wrong. But we're still looking. It would be nice. That's my take on it. It's not confirmed yet, but it's very much ongoing. Theoretically, definitely allowed. So the idea is that in the creation of matter, when the energy from the Big Bang and inflation turned into matter, some part of it went directly into tiny, tiny black holes. And or that these black holes could be left over in case of a big crunch scenario, where you have a universe that cycles. Some of these black holes can be preserved from the previous cycle, or things like that. So that there are a few reasons why you could have black holes that early on. Not confirmed yet. And kind of fringe, but worthwhile.
Fringe.
Kind of fringe.
Okay. Then you had another question, I think, about the Big Bang, yeah?
Oh yeah. So regarding the I know there was a mention of time and all that. But
Yeah, that was...
is it possible that the density of the universe affected the space-time continuum in a way that would make time be perceived different were we there?
It did. Thanks to cosmological expansion, it's not only the wavelength of light that gets longer, so it gets redshifted. You know that light gets redshifted. So you take the wavelength of light, you multiply it by the redshift to get what we see. Well, time dilates in the same way. So actually, because of the expansion of the universe coupled with travel time, by the time it reaches us, we see events play out in slow-mo, basically. So something at redshift 9, we see it happen 10 times slower.
So time redshifts.
In a way, time intervals redshift. The way we perceive it redshifts. At the time was the same. That's a confusing sentence. At the time, it was the same. Nothing felt different, but because the light has traveled so long and because the universe has expanded, the expansion has made us receive it slower than it was emitted.
Yeah, but that is because light reaches us more slowly.
It's an expansion effect, so it reaches us at the speed of light, but the amount of space in between changes.
That's good. I
Cosmic
don't...
expansion.
Yeah, no,
This is a fun topic.
It's fine.
No, I
sure,
thought of a
if...
great analogy for this, actually, the other day.
Okay.
Let's see if this makes sense. Cosmic expansion. So imagine you're in a big room, like you're full size. You're your normal size in the room, and you're trying to reach the other side of the room. The other side of the room is Earth, so you want to join your friends over there. So you set off, running as fast as you can to cross the room, but unfortunately you're shrinking compared to the room, and you keep on shrinking and shrinking and shrinking until you eventually it feels like the space in front of you is getting, longer and longer, and you're never going to reach it. And eventually you get there, and you're tiny, like super small by that point. So you look back and you think, wow, I traveled all that distance. There's no way I could have made it so quickly. But actually, now you couldn't, because now you're small. But at the time you were a lot bigger, and you managed to cross a lot of it while you were still big. If you were trying to do it now, it would take you a lot longer. And that's how cosmic expansion works.
What if the room got bigger?
That's because it's exactly equivalent. So in the case of space, we think that space is expanding. Actually, it's exactly the same as if you're shrinking.
That was a trick question.
Yeah, no. So the idea is, what does distance and time mean in that context? What is the distance? What distance have you traveled? Have you traveled the distance of the room as it looked when you started? Have you traveled the distance you feel like you're traveled? Or have you traveled the distance that now you look back and you're like, wow, that's so far? Like, what's the true distance in that case? That's one of the problems cosmologists have to deal with. They define different distances.
Because distance is relative, I guess, at this point?
At this point, it depends what you mean. Like, do you mean the distance as it was, distance as it looks now, or the distance you felt?
I'm sorry, I don't know if I'm just getting too technical, but when you're talking about distance, do you mean displacement, or do you literally just mean distance?
That's exactly the point. How do you measure it? If you had a ruler to measure it, now when you started off running, it might have looked like 10 meters. You could have measured it back then. It was quite short. By now, you're tiny, so you look back and it's kilometers and kilometers. And if you just look at your feet and you try to work out how long you felt like you walked, it depends, a different measurement
because, any measurement system is based on some fixed things that never change. So in the metric system, you have the meter, which is the distance. What is it? Like 1 millionth time the distance from Earth and the Moon, or something?
No, it's
like that?
1 step of Napoleon.
What?
The meter is 1 step of Napoleon.
No, that's not true.
That's what it was originally.
No, I think it is it has something to do with distance from the Earth. And
not in the definition. Well, Napoleon defined the meter.
I may have read it on Wikipedia, so it's not.
I think the official definition of a meter is how far light travels in 0.000 so on as many zeros, 0.125 seconds.
Sure.
Well, whatever.
But the point is that in my analogy, you are running at the speed of light. No, the analogy is you are light and the space is expanding.
What I'm saying is, the problem is the space is expanding, because as long as you have a fixed frame of reference, even if you're big, a meter is still a meter. It will look smaller to you, but it's still objectively a meter.
The problem is your meter that you're holding in your hands is shrinking at the same time as you are.
Exactly. So the problem is space shrinking or expanding.
And the other problem is experiments with Bose-Einstein condensates slowing the speed of light down in extreme low temperatures, so that's not even necessarily a constant.
No, the speed of light can definitely be slower than C. We've known this since the speed of light was worked out. In other mediums, the speed of light slows. The speed of light in air is lower. The speed of light in water is even lower. So there's nothing too strange about that. Light at its core is an electromagnetic wave, and it can be impeded by a whole bunch of things. Anything that has an electric field, like all atoms do. Atoms will always interfere with light, because light is electromagnetic radiation. It's a field.
It's because of that the Cherenkov radiation can happen in nuclear reactors, isn't it?
It's related.
Mm-hmm.
Okay.
Light can be slowed. That's not a big deal.
No, I know that. So...
Yeah, so in this analogy, kind of the same happens with time, right?
Yeah, it just makes it really difficult to, concretely say, hey, this took this long, or this was this far apart.
Yeah, like, what do you mean?
Mic on.
Made it that far, basically. So the spacing between when you arrive is suddenly a lot longer than the spacing between you when you've set off. So the time interval has also expanded.
Yet, we still use to talk about the age of the universe in light years. So we say that the universe is 7 or 8 billion.
We don't talk about size in light years. It's because it's not an easy conversion to make. Actually, cosmologists only use redshift.
Well, light years is a measurement of distance.
Yeah.
So it is size.
Yeah, that's why we don't use them to talk about the size of the universe. It's a good way to answer the question when the public asks you, how big is the universe then? Then you have to think, what do they mean? Do they mean how big it was when it set off, or how big it is now? Because that's a completely different answer.
Yeah, well, then you just throw a big sounding number at them and they go, ooh, ah, and they still don't know anything.
Well, 13.7 billion light years is how long it felt like the light traveled. That's how long the light has traveled to reach us. So it's perceived distance by the light.
But it's not literally counted in seconds as we perceive now. It is that number.
No,
it's just
time was the same in the analogy. Time is the same. It's how long they felt like they had to travel, except by the time they reached us, they had shrunk a lot.
Right.
Okay. So they may have felt like it was like 1 kilometer instead of 13.8 billion light years.
Well, here's an analogy. So when you're flying in an airplane, if you have a wind blowing against the direction of your travel, you don't notice that, like, just looking out the window. You got a constant airspeed, right? But your ground speed might be different.
Yeah.
So perceived, you've traveled this amount of time through the air, but if you got a tailwind, you'd travel, significantly farther over the ground than if you had a headwind. Yep. And so the light doesn't know how far it's come. It just says, oh, we've been going for about this long.
Pretty much. That's a good analogy. The light knows how long it's been going for.
Right.
So the correct answer to that question would be to answer it in redshifts. The universe
in redshifts.
In
redshift, the CMB is 1,100.
So the universe is 1,100 redshifts old.
And how you translate that into distance, it depends what you mean by distance.
Okay, so that is, everyone who is listening, that is how you will answer from now on to that question. Instead of using the boring 13.7 billion light years, you're going to answer in redshifts and sound even smarter than the peasant who just used light years because light years are for peasants.
Thing is,
real scientists reason in redshifts.
It's just easier.
Sure.
I'm one of the people that will actually take a note of that. What was that number?
1,100?
Quiet?
Yep.
1,100 redshifts. And if they ask you, but what does it mean? Well, that depends on what you mean.
Then you just snort at them derisively and look down your nose.
Of course.
Yeah.
I could put my glasses on, put them purposely too far down my nose, and then push them up.
And the next
actually.
And the next step, as Shoba just demonstrated, is when they ask you after that, but why don't you use, billion years? Oh, because using redshifts is actually easier. So that's the next step of...
I'm an observer. Redshift I can measure. Distance, I don't have a ruler that goes up to the start of the universe. Redshift is easy to measure.
And time is meaningless.
Well... time is a problem.
Distance is meaningless in this case.
Well, distance and time are the same thing.
Yeah, we're going deep now. Anyway, we're talking about the expansion and Selfish Pie, this is you.
I didn't want to just blatantly ask it, so I just put it down if we ever got into the topic.
I haven't read it, so I don't know what is it about. I read words like space-time and expansion, so I guess we are in topic. Ask it if you want.
Well, I'm just going to read it out because I'm probably going to mess it up myself. When it comes to the expansion of the universe from the moment of creation, the topic of expansion of the space part of space-time is commonly covered, but what about the effects of the expansion of the time part of space-time, i.e., what would you describe the effects of an expansion of time as being, rather than space?
I'm not sure I like the use of creation there, but go ahead.
That's fine. Well, matter was created from energy.
Okay, fair.
I don't like it easier, but
anyway.
It's just easier for me to say that rather than t equals 0, as in
It's
time
just
equals
me
0.
being it's just me being anal. Don't worry.
Well, the important thing to understand about the expansion is that to you, everything feels normal. So you're running across the room, you don't notice your hands getting bigger or your feet getting smaller. So the laws of space are the same in your vicinity. The speed of light is the same, and the passage of time is the same. The difference is only once you reach your destination and you try to compare what you felt to what's happened on the larger scale. And that's where both space and time have changed. The speed that you perceive events far away has slowed down, and their distance compared to you is a lot larger. I don't know if that answers it. Time doesn't slow, only our perception of faraway events because of expansion. In the same way as space extends, but to someone local, they don't feel anything. Suddenly, at the scale of the Milky Way, even at the scale of the local group, we wouldn't notice any effect. It's only when we compare what we see to the other galaxies out there, compared to us that are getting further away, and we perceive them in slight slow-mo.
Okay.
But they feel normal over there. It's only a perception effect.
You know, sometimes it's really hard to wrap our mind around concepts like this because we like having reference frames in our lives. You know, it's hard to even conceive the fact that in the end, it sounds like a cliche thing to say, but everything is relative, quite literally.
Mm-hmm.
So it's...
Apart from quantum mechanics emission levels, they're fixed and they can never be different.
Well...
Well, that's because quantum mechanics is weird, but...
Yeah.
We like classical physics, but we need quantum physics.
It's a good frame of reference, that's for sure.
For now.
For now.
For now. Anyway, we have other random questions here. Yeah, Shaky Dog has another one, but I'm going to...
I think I saw some in the astronomy chat earlier.
You did? Wait, let me check, because I was checking the... well, there was a few... There was a discussion going on earlier in the astronomy channel in Fleetcom, and I was indeed reading some pilots having some weird ideas, but I didn't see any actual questions. If you guys saw any,
okay.
Please do let me know.
No, I just saw activity earlier. I wasn't paying
But
attention.
I see that there was someone mentioning that space doesn't expand faster than the speed of light.
Depends what you mean. That's always the problem.
Why?
Well, then there's the bit that with the speed of the expansion of the universe, what might be technically within range, like we would have an event horizon where the speed of light is a constant, but due to us moving and other things far away moving,
but
our combined relative motion is greater than c, and therefore...
That's the point. I thought that, you know, the speed of light itself is constant, but that doesn't apply to space. So if everything is expanding, we will end up going farther away from everything else faster than light, but we're not actually moving. It's the space that is expanding.
Yeah, you're shrinking.
So we're not breaking the law of speed of light, but in practice, we are.
Yeah, you're both right. So it's the combined effect. So we're getting slightly further away from, say, Virgo, and Virgo's getting slightly further away from the next thing, and so on and so forth. So when you combine all these effects on the very, very large scales, it can really be any number you want, because it's not space-time itself that's stretching, it's only a small increment in every small bit of space-time. It's actually the expansion is very, very small.
But if you take 2 points very far apart, they are getting away from each other faster than light.
Yeah, they are. Compared to us, physically, they are. But that's not forbidden. As you probably know, with the speed of light, it's really saying you can't travel on the surface of space-time at faster than c. Basically, the space-time will slow you down until your mass gets so high that you can't accelerate anymore. So it's really a rule about not being able to reach that speed or go further if you're trying to travel along physically. But that's not what's happening here. It's just a tiny stretch that accumulates over enormous distances. So nothing's trying to travel on the surface in that sense. So an expansion like this is completely allowed by GR. There's no problem with it. It's like if gravity was only slightly repulsive. I think we covered this about dark energy. So gravity attracts when things are close by, but what if when things are really, really far apart, gravity starts to push them away from each other? If you just put that in, everything makes sense. You get an expansion, and no space-time is actually being torn or anything. It's that over large distances, everything's expanding and pushing each other apart.
Okay. Yeah. I don't see any actual question on that channel. But we had a question from Captain Comeback actually, and he is rightly so pushing me to ask it because he was actually the first one to answer a question about tonight's show. He did link a video that links to previous week's topic about quantum physics. We don't have the time to watch it now, but there is another question still from him. And let me just check. Oh yeah, he's asking if there is any connection between population 1 stars that were supposedly super duper massive and died very quickly, and the super duper black holes that reside at the center of many galaxies.
Ooh, cool question. Oh, that's a great question. So we're talking about these early quasars, so the ones in the first billion years that have so much mass onto them. They're already huge and they're eating even more, so they're already extremely bright by that point. And how did they get so big so fast? That's a great question. And what he's asking about, could it be linked to the super massive first generation of stars? Could that be how we got these supermassive black holes from the remnants of those stars? That's actually one of the 3 leading theories for how you get black holes to be so big. So we actually don't know. There are 3 competing ways currently being considered for how you get a supermassive black hole to already inhabit a galaxy. And one of them is that this first generation of stars, which confusingly are called population 3, even though they're the first because it's numbered backwards. Don't ask me why. The first generation of stars were super big, probably hundreds or thousands of times bigger than the stars we see today, even the blue giants. And they managed to be so big because they were completely pure. So the more impure a star is, the more carbon and pollution it has. If a star is very polluted, it can cool off much more easily. So it's able to take the heat from the inside of the star and emit it around it much more efficiently if it's polluted.
So that's what they call metallicity, right?
Yeah, metallicity. So it's metal line cooling. It's the most efficient way to cool down a star. And basically what stops your star getting any bigger nowadays is that it just, how hot you can get balances how much mass you can support. So the hotter you are, the more random motion you are, so the more you're going to resist gravity. So if you're a lot hotter, you can support a lot more mass. You can push it away with your heat. And that's why very pure stars should have been able to grow a lot bigger than the ones much later. They would have been able to sustain a lot larger masses. But we don't really know how they died. So the physics involved is kind of hard. So we don't know if they would form directly into black holes when they die or a special type of supernova. And some people say they're so massive that when they eventually die, there is nothing left at all. They just blow themselves apart completely with no remnant. But one theory says that if they do collapse immediately to a black hole, those first black holes would be a lot bigger than what current stars leave behind. So those can serve as the seeds to grow supermassive black holes early on. That's one way of seeding them.
Okay. Yeah, that was an interesting question, actually.
And to quickly finish, the other two ways are directly from a big gas cloud. So I think if gas clouds are very pure, they might not even go through a star. If you get a gas cloud pure and big enough, it will just immediately make a black hole.
Okay.
So a direct gravitational collapse. And the last one is a cluster collapse. So you get many, many small stars, but in primordial conditions, they will all basically collide with each other and make a huge black hole seed that way. So they're all being looked into. They have pros and cons. We don't really know. One of them must be true.
I guess more observations are required.
Yep.
Is it also possible that a Earth-like world, a black hole orbits?
Orbits, sorry.
Yeah.
Say again?
Is it possible that a Earth-like world orbits a black hole?
If there's a chance of Earth-like worlds orbiting black holes.
Later on, why not? Earth-like worlds, maybe. I'm not sure life could develop on them. It's a bit tricky. Well, early on you couldn't, because it takes a long time to manufacture enough elements of life.
Well, Earth-like worlds, by definition, have life, at least, vegetation. So, I mean, that's how you define an Earth-like world.
Yeah, then
it's
probably
just that
not.
It's just a Earth without humans. The way it is depicted.
Then probably not. The environment of a black hole should be pretty violent. Maybe if you had a small black hole, like in a binary with a normal star.
Yeah, you could have a main sequence star and a black hole.
That might work. But just a black hole, you think you'd be hard-pressed.
But you have no light, you have no anything.
It's like in Interstellar, right? In Interstellar, they have worlds being heated by quasar light.
Wow.
I don't remember that.
Effectively, the one where they go down and time is really slow.
Yeah, I don't really remember very well that movie.
I mean, it's
oh yeah,
sci-fi.
so so
maybe.
they have the black hole, and the planet's orbiting so close to the black hole that it's got the really high time thing.
Yeah.
Time dilation due to general relativity is increased so severely because of the fact that it's so close to the black hole that essentially 7 years passes for every hour they're on the planet.
Yeah.
Which makes
that
it
amount
curious.
is a bit exaggerated.
Yeah.
The
Which
amount
makes
of
it
time
curious
dilation is too much.
How are they even in a stable orbit around a black hole that close? And how is there even an atmosphere on that planet?
You could. It's a bit delicate. I'm not sure how long it would last, but it's not completely forbidden, I guess.
No, but then
just enough light.
Then there's this thing where could there be enough radiation emitted that to our perception it looks fairly tenuous, but to the perception of the person on the surface it would be plenty?
Also that, you'll have a distortion of how much... Maybe you'll have a bit of distortion of how much light you perceive. I guess in the movie they were actually heated not by the black hole or by a jet, they were heated by the accretion disk of matter while it was falling into the black hole. So the matter got heated so it emits light. That was their substitute for a star.
Yeah, that doesn't sound safe, but...
Definitely not safe.
At least not in the long run.
Sounds like a lot of X-rays and other unpleasantness.
But it is not completely out of the question, so...
Yeah, why not? We haven't seen them. But
fair enough. I mean,
and again, it's kind of hard to spot planets around black holes, what with our main system being transits.
We haven't seen dragons either, but...
The most exotic world we found was a potential world around the pulsar.
Oh.
But that's not. I don't think that's 100% confirmed.
Wasn't the first exoplanet discovered around a pulsar?
That was the claim. That one was wrong. It was wrong in a very funny way because they noticed, the dip in the star's luminosity, that's how we perceive planets, right? They pass in front of the star. So
transit photometry.
And they were like, okay, well, the brightness dips exactly once a year. So I guess this planet has exactly a period of 1 year. And then they were like, wait, that's exactly the same as the Earth. So could it be we haven't corrected for something correctly that changes on an annual period? And yes, they had forgotten to correct for something. They were actually just seeing like the motion of the Earth compared to the star. That was causing it to dip slightly. It was a bit embarrassing.
Okay.
So that one was a false start.
Yeah.
It was the first claim of an exoplanet. The actual first exoplanet found was Pegasi 51b.
Oh, hey guys, we discovered an exoplanet. Hey, call the press. Oh no, wait, that's actually us. Okay. No. Guys.
Congratulations,
guys.
you've discovered Earth.
Sorry, guys.
Not right.
Pretty much, yeah.
I feel kind of bad for them, but yeah.
I mean, I hope they laughed it off, but
No, they kept trying on reproving it for many years, actually.
Whoops.
No, it's not really us. It must be something else.
Yeah. Anytime you got something that's exactly equal to something on Earth, I would say really go double check it, because chances are pretty damn slim that you'll have something orbiting a quasar the exact same period as you have something orbiting
Hey, it orbits exactly 1 year. I think I can see Africa, but I'm sure it's not our Africa.
That's just a coincidence.
Yeah.
Yeah.
Oh, yeah.
Difficult stuff.
Okay. See, you need to be very careful when you do science, otherwise you look ridiculous, right?
But I think they might have a real one now, while they're on the pulsar. I'm not sure. I'll have to check that.
Oh, hey, I can see from my house from here.
It's not your house. It's very similar to yours, but it's not yours.
So, I just thought of a good question. Is there any... Would there be any reason for a space-based telescope to do the type of research into early universe stuff, or would that just be exotic and expensive?
No, yes, absolutely. That's the best way to do it, and it's exactly what we're about to do. So thanks for asking. That's what...
About to do.
About to do.
Well, let's not be optimistic here.
You can put out a GoFundMe?
We were about to do that a few years ago.
No. Both the US and the EU are rushing to fill this space right now. Because observing the early universe requires a lot of infrared spectroscopy. And infrared spectroscopy is extremely hard to do from Earth.
Oh, right.
So,
and I imagine...
it's super contaminated by the atmosphere. Yeah.
And I imagine with the Hubble kind of being on its last reaction wheels, you're definitely trying to get something else up into the sky at this point, right?
Yeah. So also the Hubble didn't see very much infrared, only a bit. So the successor to Hubble, which is the James Webb Space Telescope, which should be launched maybe next year.
It's going to be launched in 2 years, and if it's not, check back to this statement.
I heard the rumor.
I mean,
that it's actually... Don't repeat this. It's actually 6 months ahead of schedule.
Hooray!
Don't repeat this. You're just saying it on radio, but sure.
Well,
it's also being recorded, but don't repeat it.
Guys, it's a secret. It's top secret.
Okay, you can repeat it, but don't jinx it.
Right. So I'm actually like I'm
305. It's a secret. Don't spread it.
I am definitely rooting for the James Webb Space Telescope because frankly it's awesome and amazing and it will be the biggest telescope we've ever launched, and also the science. Who doesn't like science? But it is kind of sad that it's been delayed so much. Like it should have been launched according to things in like 2016. I don't know.
Yeah.
But I'm all for it, and I really hope they get it up there soon, because it's pretty awesome. Like, hell, just the way that mirror origamis itself and everything is just amazing.
Well, it's better that they're sure about what they do, because once you send it up, it's going to be hard to, recall it back and fix it if something goes wrong. Mm-hmm. But I think it won't be
the only one, though. Like, a lot of other countries are sending their own infrared things online. So Europe has the amazing Euclid satellite that's going to image infrared too. To me, that's even more useful than James Webb. Sorry, NASA.
So
Europe will also have the ELT.
But I read that XKCD confirmed it's going to be in 2026, right? The launch of the James Webb.
Yeah, I saw that.
So
that means it's confirmed. Right?
Would a constellation of smaller satellites be useful, like using the multiple telescopes thing to get higher resolution? Would that be like something that would be worth doing or not?
For infrared, not really. So basically, the longer wavelength light you're interested in, the larger collector you need. So a bigger mirror, or if you can't make a big mirror, you use multiple telescopes and you combine them. But for visible light and infrared, you don't really need to do that. You can just build the damn things. Big mirrors. For radio stuff, like we were talking about earlier, the 21 centimeter background, that you really need a big array. Actually, they're currently building one that's 1 square kilometer covered in dishes.
That's nice.
Square kilometer array. Great name.
What? Oh, that's the name.
Yeah.
Okay.
Well, I'm just curious about, like, I know a little bit of a slightly off-topic-ish segue, but with the success of the Marco A and Marco B CubeSats in the InSight lander thing, would it be possible to have like a really cheap like radio array launched with fairly sensitive like deployable radio dishes on a large constellation of something like CubeSats for sort of short-term observations and stuff like that, or is that just a silly idea?
It's possible. I don't think you would gain much compared to doing it on Earth, because one of the biggest problems when you combine many things instead of using one big mirror is that you have to combine the light from each of them very quickly and very accurately. So you can't afford delays. So they have to adjust it all the time, even on Earth, to get the combination of light just right. If you did it in space, you need a technician there.
Well, would you be able to collect the data and then use a simulation model with a very accurate timepiece to calculate exact times of reception and do it like that?
Actually not, because the trick that works to combine the light in these cases is a quantum mechanics trick called light phase.
Oh.
You can't store it. You have to make the light interact with all the other light.
Oh, right.
So in things like the square kilometer array, they actually have big optic fibers to slow the light so that they can control how it gets combined with the other light from the other dishes.
So it must be in real time.
Yeah.
You can't do it later on.
You can slow the light, but you can't store it.
Okay.
It's a tricky thing.
Question.
Ideally, you'd want to do it on the moon. That's the ideal location. No atmosphere, surface, you can have a technician there.
That shouldn't be
the dark side of the moon, right?
Yeah, away from the Earth. It's not dark, but away from the Earth. That would be great.
I volunteer to sweep the floors.
It shouldn't be too hard. I mean, the moon is basically the backyard now, right?
Well,
you say that, but
landed on the far side for the first time, like last month.
Yeah, but because we never actually wanted to. But it's not.
Well, so
if you want, you can. If you spend money, you do.
Right. So Apollo did it, and the longest, most useful mission was Apollo 17. I think they were on the moon for 3 days. But going from landing on the moon to having a permanently habitated base on the moon is a bit of a thing. NASA's planning
lots of robots there though lately.
Yeah.
If we can land robots, we can land robots that can build stuff. So NASA's currently developing this thing that can 3D print from regolith.
Yeah.
Regolith is the lunar surface, so they can 3D print using that material from the surface.
What if they build weapons though?
I'm sure they will, it's NASA.
No, I mean the robots.
The robots come out. Well, you don't have to have an AI robot on the moon. You just because you have about a second of light lag, which is we can live with that. If we wanted to do it on Mars, it would be different.
You send robots, and one day you look up at the moon. Guys, I see something that looks like a very large cannon pointing at us. What's that? Oh, it must be the robots. What? So yeah.
What's that book that Heinlein wrote where they did that? The moon is a harsh mistress.
Yeah.
Mm-hmm.
But okay, well, let's not think about that. We have more questions. Hoyer M. Now, I'm not sure if this is going a bit. Yeah, this is going to be off topic, but it's all right.
Mm-hmm.
We've been going for almost more than 1 hour now. So Hoyram is asking, what do you think, Shoba, about Hawking's no-boundary hypothesis? He's saying that his view is that he never got enough traction from other physicists, but he was exposed to it from Hawking's popular science books, and he would like to know more. And if you know what evidence would support this idea, if we could see closer to the Big Bang. I am not familiar with it personally.
I'm not sure which one he means. I don't remember Hawking's books so well.
I've only read one, and I don't remember this specific hypothesis. Hoyer M, if you are listening, feel free to expand on that question.
The no-boundary hypothesis can refer to two things. Either it's that the universe doesn't have a boundary now, or it's the universe never had a boundary. So even in the case of, if you have a primordial singularity at the Big Bang, that singularity itself already didn't have a boundary. It was already infinite. I'm oversimplifying, maybe.
So basically, the universe is infinite.
Yeah.
In size.
In size. And it comes down to this is hard to explain. So people are usually happy thinking of like a sphere doesn't have a boundary. If you walk around the sphere, you'll never reach the edge. It's kind of closed, so you don't reach a boundary. You don't reach an edge. And even when the sphere was super small, it never had an edge. It always had a finite contour. But actually, there's more to it than that. We like using the sphere analogy because the sphere is an object that we can imagine in our mind. So it's a 3D object, and on the surface it looks 2D, and it's embeddable. So it's a 2D surface that we can embed in 3D space. So we can see it in 3D, even though it's intrinsically 2D. But in maths, most surfaces are not embeddable. That means even if locally, when you're on them, the properties make sense and you can write all your equations, there is no way to embed them in a higher space. So we can't visualize them. There's no convenient way for us to imagine them in our mind. So it's more general. One example is the hyperbolic space, so a space with negative curvature. Instead of everywhere being curved down, every point that you would feel if you were on the surface is a saddle point. So in one direction it curves down, and 90 degrees it curves up. And then 90 degrees it curves down, and 90 degrees it curves up. It goes up on the sides and down from you at the front and back. And a space like that can definitely exist. Mathematically, there's no problem.
But that would fold in itself eventually, right?
That's because you're trying to embed it in 3D space instead of just understanding what you would perceive on it. And that's a big, difficult thing to explain to people, because the universe doesn't have only 3D. According to string theory, it could have a lot more, and not all of
like 12 or something, right?
Imagine.
11.
Yeah,
well, M theory is thought to have 11. String theory itself has 9.
Some version of string theory, up to 19.
So imagine something that's like a sphere, but not in 3 or 2 dimensions, but in like 11. And once you've done that, you won like life because you're the smartest person.
You can't imagine it, because It's even worse. The hyperbolic space isn't embeddable in any number of dimensions. It is never embeddable. So it's a surface that makes sense. In 2D, you can describe exactly what someone would see, what distances would look like, how you would travel on it. You can describe all that stuff fine. There would be nothing weird if you were living in that. Well, it would be weird. You would, it would curve in strange ways. But it's allowed. And despite that, it's not embeddable for us to have a nice mental picture of it.
But you say it is allowed, but the fact that we can prove it mathematically doesn't mean it exists.
Well, in GR, allowed by GR. In GR, all you care about is your local metric definition. And a negative curvature, a hyperbolic space, is completely fine with the equations of GR. GR does not care if your space is embeddable or not.
No, but the fact that it is allowed, it doesn't mean it is actually a thing.
No, I'm just building up to this no boundary hypothesis. That's the central concept. That your local space-time metric has no obligation to make sense. It only needs to be described locally.
Yeah, it is a hypothesis because I guess it is not promoted to theory yet. But Hoyer is asking if there is any evidence that would support this, that we can actually see, oh, that may imply that this is a thing.
I don't know of any specific tests you could do to check it. So the no boundary hypothesis said it was basically like this, no boundaries all along, even below the quantum scales. It was still infinite because in this sense. That is it's either not embeddable or literally infinite, and it's fine with the equations.
Okay.
And because time dilates, there is also no way of defining time when you get below the quantum scales and a whole bunch of things. So it's basically kind of a recursive Big Bang. The closer you get to it, the more time slows. Space still looks the same because you just zoom in and it's the same everywhere. So it's kind of like a recursive, kind of always getting there, but never getting there. So in that sense, the universe never had a start because you can zoom in infinitely close.
Hooray.
I've probably done a terrible job explaining it.
No, well, it's
well, it's hard to
explain. It's really not easy. I mean, it's really not easy because the way we, at least for me, the way we learn things usually is to try to visualize them in your mind. You know.
I mean, and at a certain point, we can have all these like hypotheses and stuff, but at a certain point we can't prove any of it. Like the only way you could prove it is to get outside of the universe and take kind of like a snapshot of the whole big thing without being like within it, and I don't know that that's ever going to be possible.
So at least with Hawking radiation, it made a very specific prediction we should see radiation from black holes. So I guess that's more testable, which is why we like it a bit more. Negatively curved space, so this weird hyperbolic non-embeddable space, that's very testable too. Actually, it's kind of edging in that direction. When we try to measure the curvature of space-time, it's very close to zero. But if you're asking on what side of zero it currently looks like it is, it's probably negative. But we don't talk about that. It's still consistent with zero. The universe looks completely flat. So the universe being round means if you look forward, you would eventually go in a closed loop, right? Like a sphere, like a 3D sphere. The universe being flat, well, it's just flat, like a grid. And then negative would be this strange hyperbolic space.
The fact that the universe is flat doesn't mean that the Earth is also flat.
It does not.
You and your flat universe theorists.
I thought I had got you there, like, to confirm that everything is flat.
Flat universe theory. No, flat lambda CDM is the current leading model.
Do you think it is a coincidence that the universe is flat? You're telling me that the universe is flat, but the Earth is not? You're contradicting yourself, scientist.
You say that, but people have worried about that so much. Like, why would it be flat? That's actually a big concern in cosmology.
Why don't you fall off the edge if it is flat?
But it
that's the
be.
thing.
The thing is, being exactly zero is incredibly unlikely. Because if you started with even a bit of curvature, with time, it would actually get worse. It would get more curved. That's what most theories suggest. Yeah.
What if it's just like blowing up a balloon, and the longer the universe is expanding, the flatter any given postage stamp size of balloon is?
Yeah, but then you should be able to see curvature at least early on, at least in the CMB, in those first thousands of years. But even then, it was completely flat, and it was so close to being completely flat that if it was a balloon, it must have been inflated like a billionfold.
But what if light is following the curve and just it looks like it's flat, but it's not because the light is following the curve?
No, we use tricks for that. There are tricks you can use to measure curvature in 3D. That's a bit technical.
I'm not sure if I heard correctly. But you're saying that it is, it is zero, right?
It is very close to zero. It's consistent with 0.
And you're saying that is unlikely. That was unlikely.
It was incredibly unlikely. Yeah.
Yeah, but why? Why is that?
Well, it's like who was it? Well, it's like you just said. It's like if it was a balloon, anyway, and it was inflating, it looks so completely flat by now that the balloon must have inflated an incredibly large amount to look this flat. Right? It wouldn't just look so flat. And if it was flat from the start, that would make sense, I guess. But the problem is, of course, if it's flat from the start, then it's literally infinite.
No, but what I'm not getting is, maybe I didn't understand the start of the reasoning, but you're saying that 0 was or close to 0 was unlikely.
Yeah, right. Because that makes it flat.
Yeah, because if it was even slightly curved, it would be easy to detect.
There's literally no reason for it to not have ripples in it, but it doesn't have ripples in it at all. It doesn't have any discernible features.
But if it wasn't like it is now, we would say, oh, it's not 0, it is actually 10. It was very unlikely for it to be 10, but it is 10. Isn't it just some sort of anthropic principle at this point?
Not really. If it was an actual value, then you could say in the past, when it was less expanded, it was more curved, and you could trace it back that way. You'd have a way of tying it to expansion. If it's exactly 0,
it may just be, it's 0 because it has it is a number that has any chance of existing as any other.
No, look at it like this. It would be like
sending 0.0000001.
It would be like sending a probe to Proxima Centauri and finding a planet orbiting Proxima Centauri that was a perfect sphere to within fractions of a millimeter. There's no reason for it to be that way. Sure, it's entirely theoretically possible for it to be like that.
There is no reason for it not to be that way.
Yeah, there is.
Not really.
Right, but 0 is a special number. 0 is not just a number, right? 0 is telling us it's not curved either way. It's a very, very delicate balance between falling over in either directions.
Right, it is delicate, but if you... It's like, if you put 100 numbers in a bag, including, the chances of you picking out 0 is the same as you picking out number 7. Okay,
but it's
0
not
is special, but it's still, it's still one number among many.
But that's the point. It's like you walking up to a pool that has never had a ripple in it. Like the chances, like every event in the early universe should have been causing like things to happen. If it's anything but dead flat, right? I don't know. It's kind of hard to explain, but
it gets even worse for our case, because when we observe the CMB. Basically, we observe the CMB in every direction, right? In front of the Earth and behind, 180 degrees opposed, okay? And these two bits of the CMB seem to be exactly the same temperature. But if you know any physics, you know that if for two things to be the exact same temperature, they must have once touched each other. But these things are too far apart to have ever touched themselves at the current expansion rate. So by the time matter was created, they were already too far apart. They never touched each other because they're opposite you in the sky.
That just hurts my brain.
Wait. I mean, everything touched everything else at the Big Bang.
No, because back then there was no matter.
Matter was created after the Big Bang, and it wasn't created in a singularity. The Big Bang might have been a singularity, but matter creation wasn't in a single point.
The CMB itself
there was an input of energy, which gave rise to matter. That energy, we're not sure where it came from, but that wasn't at the singularity. It must have been a fraction of a second later.
But in that amount of time, things were far enough apart for those two chunks we're seeing to not have been in contact with each other.
Yeah.
And therefore, for them to be the same temperature is the weirdest thing ever recorded.
No, but you see the CMB being the same temperature.
Yeah.
That's the point.
An object. The CMB is not an object.
But the CMB is like
in these two places. It was created exactly the same. Wait.
But the CMB is like the fingerprint of things that happened before.
Yeah, exactly. So they had thousands of years to homogenize, and each part of the CMB homogenized with its surroundings, but somehow even parts that never had a chance to touch each other could homogenize in that time. So this observation, plus how flat the universe is why people suggested inflation as a solution. Those the first two big arguments for inflation. That actually, right at the beginning, after the singularity, the universe was expanded enormously. Just after these small fluctuations of temperature appeared, it expanded enormously. That made it look really flat compared to us. Plus, these fluctuations were there just before the inflation.
That, or we just horribly misguessed the age of things.
Kind of, but I mean, we kind of know how fast gas cools. I mean, that's tested in labs pretty quickly. The CMB temperature is not that crazy. We can do it in labs.
What about the chances of some sort of massive gravitational ripple caused by the formation of everything, causing enough of a distortion in the space-time continuum to slow everything down?
That's basically what it is. I mean, these inflated ripples. It's basically you get the first quantum fluctuations. If you remember, 2 weeks ago, we talked about quantum physics, how in a vacuum things can pop out and disappear continuously.
Well, last week.
Right.
That wasn't it time last week? Okay,
No.
maybe last week. So
Yeah.
So if some of them appear and then they get massively inflated, suddenly they're huge and they're leaving huge imprints in your space-time and huge imprints on where the matter is going to be created and huge imprints on the CMB. And that's exactly the imprints we see on the CMB.
The good old butterfly effect, huh?
Yeah, so you inflate for something small, it affects the entire universe. An inflated quantum fluctuation.
Okay, this is getting too hard for me. Yeah, but we had another question from Ganlan, and it's a question that he submitted last week, but it wasn't relevant to quantum physics, so we postpone it. And well, this is about black holes. It's not really exactly relevant, but it does sound interesting. He is mentioned that in Star Wars there is a cluster of 4 or more black holes called the Mo.
The Mo.
Yeah. It somehow hides a planet in the middle of them with no bad effects, apparently.
Oh, that thing. Okay.
He's asking if you could guesstimate how fast would that planet actually be torn apart, being so close to so many singularities. We did say before that it is technically possible for a planet to orbit a black hole, but is there a way that it can be in the middle of them? I guess in a sort of it's not even orbiting. I mean, if the black holes are around, it is being pulled by all of them, but somehow it is exactly in the center, so it stays still.
Theoretically possible. I'm looking for information on how far apart.
I don't know if the Mo is like that. It's just how I'm picturing it in my mind. I am familiar with it.
If I had to take a guess at it, and there's going to be a lot of assumptions here, if you were talking about, just talking about the black holes for a second, if by the planet orbiting the black holes, you mean that the black holes were in a mutually perfect system where they were, if you imagine their orbits as a circle, they were exactly 90 degrees from each other. There would therefore be a barycenter at the middle, and therefore then the planet would be at that barycenter. If that's what you mean, then I would say that would be able to act as an unstable Lagrangian point, and then it wouldn't necessarily get torn apart. I would say it would just fall into one of the black holes due to the instability.
Well, unless they were all exactly the same mass.
Well,
there's other configurations though. Like you could have a slightly heavier black hole at the center, and two of them in Lagrangian resonance points around it. And that would create a point behind the two of them, like in a lozenge. So you could have a planet there. That would be a stable Lagrange point. That's one way. And then the fourth one, I don't know. You just put it in orbit around the first.
But as far as the Star Wars thing goes, being a qualified Star Wars nerd, it's my understanding that when you're traveling in hyperspace in the Star Wars universe, a gravity well will knock you out of hyperspace. Since black holes have relatively large gravity wells, they would be somewhere you'd try to actively avoid when traveling in hyperspace, which means that a planet in a black hole system like that would be, by its very nature, very difficult to discover for somebody traveling in hyperspace because of the dangers of skipping just too close to a gravity well of a black hole and getting ripped out and not being able to re-enter hyperspace. So
you'd have to go at normal propellers instead of hyperspace.
Right, which would take forever. And so like from that point of view, yes, it's entirely possible to have a planet hidden within a group of black holes. Now, whether they portray it accurately or not,
I reckon you could still scan it. No.
I mean, maybe I don't know this piece of Star Wars lore, but maybe it's not like it is in orbit. It's just a planet in a system with a lot of black holes. Maybe there isn't even another normal star. It's just that there's also a lot of black holes.
Well, according to Wikipedia.
But Wikipedia is wrong.
No, Wikipedia.
No, Wikipedia.
Wikipedia is reliable, yeah, of course.
The Mo is an unstable and mostly unnavigable cluster of black holes located near the planet Kessel.
So it's unstable. Okay.
It's unstable, so the black holes are being flung around each other chaotically. Yeah, in that kind of situation, the planet would not live. You would be hard.
I know. Ganlan is saying that apparently there is no ill effect to the planet. That doesn't sound like what Wikipedia is saying.
If you had like a tiny way of pushing the planet ever so slightly to rectify its course, it wouldn't go unstable that quickly. It would be stable for a few million years at a time, and every million years you'd have to adjust it a bit to put it in a newly stable orbit.
Yeah, that's all right.
To be fair, is within the realm of Star Wars, because there was some books written where they had like whole planets getting pulled through hyperspace and all that. So yeah, that's cool. They got planetary repulsors.
If you remember to set the alarm clock every million years or so.
Yeah. Nudge it ever so often.
So long as you don't forget. Okay. We have a question from Twitch or YouTube. Is it Twitch or YouTube, Michael? I don't know. Looks like the YouTube icon, but
I think it's YouTube.
Yeah, it's YouTube.
Yeah.
Sorry.
Yeah, we have Mad7 on YouTube asking if you could briefly touch on the fact that gravity is usually considered a weak force because it looks quite strong near black holes.
Weak force. It is considered a weak force, that's true.
Have you ever seen...
yeah?
Magnets. That's all I'm going to say. Magnets.
Yeah.
Not a weak
Have you ever
force.
seen magnets?
I have a neodymium ball magnet and two thick aluminum cylinders, and they're perfect for demonstrating Lenz's law. Oh, I love it.
So gravity is a weak force, basically because it takes so much mass to make anything happen, as opposed to something like magnetism or molecular bonds.
Yeah, so it's weak out of the four fundamental forces. So in addition to gravity, we only have three others. There's a electromagnetic force, the weak force, and the strong force, confusingly named. And all of these ones are about 10 to the 30 times stronger than gravity. So 1 followed by 30, 0 times stronger.
So there is a weak force, which is not gravity.
Yeah.
So gravity is the weakest force.
It's the weakest force. But it wins on separation. So for distances, it wins in the long haul, right? Because the other three fall off a lot faster. So gravity, and they have a limit to their action. apart from the EM, debatable. The strong and the weak force have a limit to their action. They don't keep acting at any distance. It really, really falls off super sharply. And so does magnetism. So a magnet, the size of the Earth and a magnet the size of the Sun wouldn't attract as much as gravity does. It falls off a lot faster. So gravity wins on distances because it doesn't fall off. It applies to everything. But like you said, if you compare it to magnets, you have two tiny magnets. They attract very strongly. If you make the two same magnets just out of matter, they will not attract due to gravity. It's actually 10 to the 30 times weaker than that. 10 to the 40-ish. It is extremely weak on those scales. But it wins as a unifying force. It can keep bringing things together. It doesn't have a limit to its range of action.
So it looks weak, but it is weak on the short scale, in the small scale, but it is persistent. It doesn't give up as easily as the other forces. Oh no, that guy is too far. I'm not feeling attracted to it anymore. Well, gravity is, he's into long distance relationships.
It's like the Chinese water torture of getting stuff done.
And gravity also likes everyone. Gravity is all inclusive. So if you think of electromagnetism, magnets, they only attract the plus or the minus. Electrons only attract protons. Protons don't attract each other, they don't like each other. If you're trying to build a universe only with electromagnetic forces, a lot of your stuff isn't going to want to stick together. It's always going to have a mixture of attraction and repulsion. You couldn't make a black hole out of electromagnetism. But gravity likes everything. It's a long-distance relationship kind of guy that also has no limits on who they're ready to date.
But it's also quite chill, so it's not possessive, It lets you go if you really want to.
Yeah, exactly.
I quite like gravity as well, because it gives me a reason to say that at least someone is attracted to me.
And it's always okay with you sticking around.
Black holes are
Well, that was that was sad, but I understand what you mean. Still,
and yet we laugh.
It's good to get questions from YouTube as well, because I don't know how many viewers we are numbering now, but it's great to have some viewers there too. We have few more questions which were not asked in the interview channel. Shame.
Or at least astronomy.
No, not well, I saw them by chance. It's still Captain Comeback. A whole string of questions. We need to be quick because we are almost out of time. Let me see. Oh yeah, he was asking earlier if the Milky Way can be called the first generation galaxy, or we are made of remnants of other galaxies.
Easy. All galaxies probably have an equal claim to being the first, because all galaxies were made from tiny, tiny blobs of stars. Blobs came first, and then the blobs came together to make galaxies. So it's hard to say when the Milky Way started as a thing, because originally it was scattered everywhere. So which one was truly the Milky Way, this blob or one of the other 100 blobs? But eventually all the blobs combined. So star formation in the first generation was very, very scattered all over the place. The Milky Way disk, so the actual main disk orientation and shape, that was in place about 2.8 billion years after the Big Bang. After that, it had a few major collisions, but it always restored itself.
Wait. So let me stop there.
Yeah, okay.
We are not peasants.
Yeah, okay.
We think in redshifts.
Yeah.
So how many redshifts ago that was?
It was at redshift 1. God, I have to do it backwards.
You're telling me you don't know? Are you telling me you're a peasant?
I'm a peasant.
No, she's on a higher plane of thinking, and she has to think down to your level.
You still think in light years? It's 2019 and you think in light years.
But it's not a distance, it's the age of the Milky Way.
Wait a minute. Oh, it's 2019.
It's archaeology.
Actually, you're right.
Yeah, so it didn't happen far away. It happened here some time ago. That's why I'm thinking in years.
Okay, I was trying to make a joke. It backfired spectacularly. I'll shut up.
Around Redshift 5.
I'll let someone finish the
Redshift
segment
5.
because go ahead.
But
So that's when it had the disk, at least from that point. Then it had a few major collisions with the disk stayed.
okay, but what's 2019 in Redshift?
0. It's 0.
Okay, well, that was easy.
Yeah, local universe is Redshift 0, not Redshift.
Huzzah.
Okay, what is 1 year in Redshift?
Still 0.
It's just not measurable.
Almost
It's in
zero.
noise.
No, it's actually 0 because expansion doesn't work on the size of a light year.
It's in the
To
noise.
see
Like
expansion, you have to go to like the Virgo cluster. Just like when you start seeing Redshift, and even then, I mean, it's not an average trend. You have to go a bit further than that to really start seeing consistent Redshift.
Right.
What's the Redshift of Virgo? Probably really small.
Let me check, because I believe that there were other questions. Guys, help me out if you see
I'm
something that
I saw one. Supermassive black hole creation days are long gone.
Right.
That's not a question.
It's true, I guess.
Captain Comeback had one question. Is the Milky Way an original?
We just answered that, Michael.
Yeah, we were
All galaxies are
Good
original.
morning. How are you?
Wait.
You want some coffee?
Some galaxies
Yeah,
may
I
be
probably
ultra
need some
late
coffee.
comers.
No,
but that's
sorry.
about it.
I had to go. I was on the phone.
No, it's fine. It's getting late. I understand.
No, so I mean, the
No,
bottom line
not
was
that
all
late.
galaxies have equal claim, but except some of them that might be particularly late comers to the party. We see some of them too, but they're rare.
What will be happen if Andromeda and Milky Way will collide?
The solar system would be fine because stars wouldn't actually collide with other stars, so the two galaxies would kind of pass through each other and distort and merge. But stars are actually very fast-paced, so they would basically just miss. The stars would miss, but the overall galaxy would combine.
Still, it
How
would
can you
make
say
for
that for
one hell of
sure?
a sky.
So we've seen it happen. We've seen it happen with other
night sky
collisions
would-
of galaxies.
Night
Nice
sky
guy
would
Andromeda.
look awesome.
No. I mean, you've seen
look
it happen,
great.
but can you dismiss entirely the chance that when this happens to us, it will actually a few stars actually collide, and one of them can be ours?
Well, by that point, our sun will be out of fuel, so...
I would say you probably can say that stars colliding will not happen when the galaxies merge, simply because of angular momentum. So the two stars moving towards each other will be affected by gravity of each other,
Yeah.
and that gravity will perturb each other's path in such a way as they will not collide.
Star-on-star collisions are incredibly difficult to arrange.
Yeah,
would
so they
prefer to swing.
might swing by each other and start whipping around and fall into orbit and eventually merge, but they won't like run head on like two cars on a freeway.
I mean, not even if they come into orbit of each other, they'll just become a binary, so that they don't even care. The only
Yeah.
cases you get star collisions is where you have a lot of stars in a very small space, but then the chaos is large enough. So like a small nebulae colliding. Maybe then. But
Or like,
not the sun.
Because galaxies are mostly empty space.
Yeah, I mean, we know that, of course. You can see it every day.
Or perhaps the two supermassive black holes of the two galaxies getting nice and close to each other might make a little bit of fireworks, but that's also highly unlikely.
Yeah, eventually they will. If we think eventually black holes merge in this way.
Yeah, but there's going to be like
Combine.
carbon stars by then, so we're all good. Or iron stars, maybe. Who knows?
Maybe, I don't know. Could happen quite quickly. So it's a bit of an unknown how quickly supermassive black holes combine.
You
Because
say
there's a lot
quickly.
of like gas and dust at the center, and gas and dust creates friction. And if there's friction, they can lose angular momentum and actually merge faster than they would. So it could be quite a fast process at the scale of the age of the Milky Way.
How does gas and dust create friction on something that slurps them up like a vacuum cleaner?
Because they orbit each other, but the space they're in, because you had all this feeding of Sage star in the past, the space they're in is not completely clean. So on average, in our galaxy, there is 1 atom of hydrogen per cubic meter-ish.
Right.
That's the average density of the galaxy. But in the center, it's a lot more than that, just from the leftover stuff that was eaten in the past.
So is it more just like drag more on the accretion disk that has a very minimal gravitic effect on the thing rather than drag on the black hole itself?
Yeah, there's the accretion disk itself, and then there's the larger area, what we call the torus. Sorry. So there's the dusty torus that surrounds quasars when matter falls in, and some of that can be left later. And it's like a big sphere, kind of elongated egg shape, weird thing. So there is just more material over there.
Mm.
That's why you get orbits with friction.
A dusty galactic donut.
Yeah. Well, not really a donut, more like a really tall donut. Like I don't have a...
Like a stack of donuts, but like a
Yeah.
uni stack, like a uni donut, like.
Yeah, like a stack of donuts.
But they're all one donut. Oh my god, now I'm hungry.
Yes.
Yeah, I think it's time for dinner, at least for us. It's 10:30 IGT.
No, I already had
So
dinner.
it's been... Sorry?
I already had dinner.
Yeah, well, we have not. But yeah, we are reaching the end of the show. I can't see any more questions.
I think there were a few,
have
but...
one.
Okay, go ahead.
What if Earth was in the middle of the galaxy instead of where it now is? How bright will it be then?
Like the night sky, you mean?
Yeah.
Super bright.
Just
So-
fly your spaceship there and take a look.
Is it
No, like
so-
in game, it like Elite Dangerous is a pretty good representation of that, I think.
Yeah, true.
It is, yeah. If you set the rendering to include all the stars, of course.
Well, you
Wait,
can
is that
do
possible?
Yeah.
Yes.
yeah.
I mean, if you have a good
What?
computer.
Yeah.
Well,
I
I
recently
did that
discovered it
at
myself.
least to a degree.
Hang on, how do you turn it on?
Configuration.
We'll get it later.
it requires editing the config files, but I was about to write a tutorial for that, but I haven't really got around to do that yet because
Maybe
the
interesting,
information I
though.
gathered was scattered all across the internet, so would be a
Because
trouble
some
from
people with powerful enough machines may be able to take some cool screenshots. Oh.
Not me.
Well,
Well.
if you look at my screenshots, that's what it will look like. And also, it doesn't really require a powerful machine except for the galaxy map, because it will actually, the galaxy background will be rendered from the stars that are around you, and the galaxy map will show them all at once, and that requires quite a bit of rendering power, but for the galaxy background itself, it just takes loading time and quite a bit of RAM.
Okay.
But not
Okay.
that much.
How
rendering
about
power.
16? Is that enough?
16 what?
RAM.
Gig of RAM?
Gigs.
16 RAM. 16 gigabytes of RAM. Yeah, that's enough.
Well, you guys can try and
video RAM.
let everyone
Yeah,
know.
we should probably wrap up the thing and then talk about that
Yeah,
later.
we will. We are going to wrap up. I was just going to say, because we got some news just this evening. I think that our good doctor has been invited to another radio.
Hmm.
Do you want to talk about
I
that?
already heard of it.
I don't know yet.
What do you
Interesting.
mean you don't know yet?
Well, I mean, yeah, apparently I'm gonna be on this German radio. Maybe.
Yeah, she's being shy about it.
I don't
But
know.
Yes.
no, I mean we will have
Well.
more news in the upcoming days. But
A radio view from Germany.
Yes,
yeah,
Have you ever heard of Deutschland Funk?
yeah, Deutschlandfunk is a pretty serious radio station. Well, it's
I'm not sure how much.
nationwide. It's well known. It's renowned, I would say.
oh wait, it was not supposed to be a secret.
I'm not sure. I'm not sure what I can say.
Shit.
You've embarrassed me.
I didn't know that. Okay. Okay. Let's wrap up, guys.
Yeah, well,
you heard nothing.
Only good things to know about both.
Yeah. No, Michael. Make sure to cut this part when you upload the file.
However, if any of you, by any chance, dear listeners, are in Durham this week, I will be at the University of Durham on Thursday. It's a free event. If you can come meet me. I'll be talking about cosmology and stuff.
That's the one moment I wish I lived in England.
Didn't catch that.
And if you're elsewhere in the UK, I have a lot of other dates around the UK.
Yeah, but I'm in Scotland. No one ever considers us.
Scotland is like Durham is as close to Scotland as I'm ever gonna get.
Yeah, but I'm lazy. Like, come to Glasgow, you enjoy yourself.
Or Edinburgh. Edinburgh's nice.
Oof, no.
Anyway, guys.
That's like the cliche Scotland city.
Let's wrap up here, guys. This has been Dangerous Cosmology. 5 minutes after the Big Bang, with our good doctor, Shoba, or Sarah, as sometimes she prefers to be called. And this has been Nightfall Zero, and with me tonight there's been that Michael, as usual, focusing on the technical side, Selfish Pie, Just the Raptor, and Thor Wathanson. Thank you guys for joining. Thank you everyone for listening in and for sending us questions. We don't have a topic for next time yet.
I suggest, what was it? The Fermi Paradox.
Let's expand it to alien life.
Ooh, interesting.
Well, we can start from that.
That's a good one,
of course. Yeah.
And just to specify, this is not necessarily intelligent alien life, correct?
All inclusive.
Well, yeah.
I will read up on exoplanets.
Ooh, this is going to be a fun one.
I'm gonna watch all those Isaac Arthur videos again to prepare. So.
All right. So this is the end of this segment, guys.
Yes.
Thank you again for listening in.
Thanks for listening.
Thanks for watching. Thanks for listening. I don't know if there is some music after us, some DJ, or if just the auto DJ, but stay tuned as you fly towards the next waypoint. And we will see you next week for the next episode of Dangerous Cosmology. Thank you and have a good night.
Bye-bye.
Yes. Bye-bye.
Bye-bye.
Okay, we're clear.
I didn't think I